Welcome to Lecture 4. This week we're going to start talking about differentiation. We'll cover sections 3.1, 3.2, 3.3 and 3.4 in your textbook. First, let's talk about tangents and the derivative at a point. You've seen a road sign like this. What this means is if the road goes forward 100 meters, then it goes up 3 meters. In mathematics, we write this as slope is equal to 3 over 100. This line has slope b over a. This line has slope 3 over 3, or 1. The slope of this line is 4 over 2, or 2. This line is sloping downwards. So we say that this slope is equal to minus a half. But what is the slope of a graph at a particular point? Well, what we can do is we can draw a line which just touches the curve at that point, and such that the slope of the line is the same as the slope of the curve at that point. This green line is called the tangent line at the point x is equal to x0. Now, we can draw a triangle under the green line. We can measure the slope of the green line. We say that the slope of the blue curve is equal to the slope of the green line. So, for example, if I had the function y is equal to x squared, I could draw this green line where x is equal to 1, and I could measure the slope of this line, and it turns out the slope of this line is equal to 2. Or if x0 is equal to 0, I could measure the slope of this orange line, and of course that slope equal to 0. Or this red line has slope 4, so we say that the blue curve also has slope equal to 4 when x0 is equal to 2. But how did I know this? How can we calculate the slope of a tangent line if we know a function? Well, instead of calculating the slope of the tangent line, instead we could calculate the slope of a different line. We could calculate the slope of this orange line. Now we know the width of this triangle, and we know the height of this triangle. The width, or the base of this triangle, is going to be the difference between x0 plus h and x0. And the height of this triangle is going to be the difference between f calculated at x0 plus h and f calculated at x0. So the slope of the orange line is easy to write down. The slope of the orange line is f at x0 plus h minus f of x0, that's the height of our triangle, divided by h, which is the width of our triangle. Okay, now look what happens if we make h smaller and smaller. In other words, if we move the right-hand end of this orange line closer and closer to the left end. As x decreases to 0, or as h decreases to 0, as x0 plus h tends to x0, the slope of the orange line is getting closer and closer to the slope of the green line. In fact, we can say if h is very, very small, then the slope of the green line is approximately equal to the slope of the orange line. And we have our formula for the slope of the orange line. Now, what does it mean to say h is very, very small, or h is close to 0? And what does it mean to say the slope of a line is close to a slope of another line? We've been talking about that for the last 2 weeks. That's the idea of limits. So we can say that the slope of the graph of the function f which is also called the derivative of the function f at the point x0, is the limit as h tends to 0 of the slopes of the orange line, if this limit exists. And we call this derivative, or this slope of the function f, we call this f prime at the point x0. So for example, find the derivative of the function g of x is equal to 1 over x, for x not equal to 0. In other words, find the slope of the graph of this function as long as x is not equal to 0. So we have our formula from the definition. We want to calculate g prime at x0, and the definition is that this is the limit as h tends to 0 of g of x0 plus h minus g of x0 divided by h. It's the limit of the slopes of the orange lines. Now it's just a case of putting the formula in, manipulating it, and then getting our answer out. G of x is equal to 1 over x. So g of x0 is 1 divided by x0, and g of x0 plus h must be 1 over x0 plus h. We're taking the function 1 over x, and we're replacing x by x0 plus h. Now I need this to be all over the same denominator. So just the same way that if we were trying to do a half plus a third, we write it down at the bottom. If I was trying to do a half plus a third, I would write everything over 6. I would write that as 3 over 6 plus 2 over 6. So I could add them together. I want to do the same thing here. I have something over x0 plus h and something over x0. I want to write it all over x0 plus h. Because then I can do my subtraction. I have x0 minus x0 minus h on the top, and then put everything on the bottom together. H I have here, and then x0 plus h. At this point, we can start simplifying this. x0 will cancel with x0, and we'll just end up with minus h divided by h, x0 plus h. But then the h's will cancel as well. And we'll just be left with minus 1 on the top. At this point, it's okay to replace the h by 0. Minus 1 divided by x0 plus 0, which is just minus 1 over x0 squared. So this is our answer. This tells us the slope of the function at each values of x0. For example, if x0 is equal to 2, we put 2 into the formula, and we get minus 1 over 2 squared, or minus 1 over 4. The slope of this green line, which is the slope of the curve at x equal to 2, is minus a quarter. Or, looking at the red line now, if we're interested in what happens when x is equal to minus 1, there's a typo here, we can put minus 1 into the formula. We get minus 1 divided by minus 1 squared, which is equal to minus 1. The slope of this red line is equal to minus 1. That means the slope of the blue curve is equal to minus 1 when x is equal to minus 1. So that's the idea behind derivatives or slopes of curves. Let's quickly move on and start talking about the derivative as a function. If f prime at x0 exists, then we say that f is differentiable at x0. Let f from D to R be a function with domain D and target R. If f is differentiable at every x0 in its domain, then we just say that f is differentiable. Now, if f is differentiable, then that means we have a new function called f prime. F prime is called the derivative of f. For example, differentiate f of x is equal to x divided by x minus 1. That's the same as saying find the derivative of f, or find f prime. So we're going to use our formula again. Our formula is that f prime of x is the limit as h tends to 0 of f of x plus h minus f of x divided by h. Here f of x is equal to x over x minus 1. We also need f of x plus h. Replace every x by x plus h, and we get x plus h on the top, x plus h minus 1 on the bottom. Let's put these into the formula. We need to calculate the limit as h tends to 0 of x plus h over x plus h minus 1 minus x over x minus 1 all over h. So we do the same as we did before. We're going to put everything over the same denominator. I'm going to put everything over x minus 1, x plus h minus 1. So what do we have on the top? Well, we have x minus 1 multiplied by x plus 1, just here. And then we get x multiplied by x plus h minus 1, just here. And we had an h on the bottom. I still have a 1 over h. I want to simplify this and then calculate the limit. First, let's multiply everything out. The limit of 1 over h, and then x squared minus h plus hx minus h minus x squared minus hx plus x. What can we cancel here? I have a plus x squared and a minus x squared. They're going to cancel. Minus x and plus x, they're going to cancel. Plus hx minus hx, they cancel. I'm only left with minus h on the top. So there we go. But now minus h on the top and 1 over h on the bottom, these are going to cancel, and we'll just be left with minus 1 on the top. At this point, we can replace the h by 0. Minus 1 over x minus 1, x plus 0 minus 1. And that is equal to minus 1 over x minus 1 squared. So the answer to this question is the derivative of x over x minus 1 is minus 1 over x minus 1 squared. Now, sometimes it's easier to use an alternate formula for the derivative. If we take the formula that we've been using and we substitute in z is equal to x plus h. Everywhere we see x plus h, we're going to replace that by z. So instead of x plus h on the top, I have z here. Instead of h on the bottom, rearrange this. That's the same as z minus x. And instead of the limit as h tends to 0, that is the same as the limit as z tends to x. This alternate formula, which is basically the same, is sometimes easier to use. For example, find the derivative of f of x is equal to the square root of x for x strictly greater than 0. I'm going to use this alternate formula, which I've written in the yellow box at the top. So I'm going to calculate the limit as z tends to x of the square root of z minus the square root of x divided by z minus x. If I factorize the bottom, I can factorize z minus x into root z minus root x multiplied by root z plus root x. And then I can cancel the root z minus root x on the top and on the bottom. And then I'm just left with the limit of 1 over root z plus root x. At this point, we can take the limit, replace z by x, and we get 1 over 2 root x, which is the answer to this question. Sometimes we're going to want to find the equation of a line which passes through a particular point and which has a particular slope. The line which passes through the point x0, y0, and which has slope k, has the equation y is equal to y0 plus k, x minus x0. I'm going to use this formula in the next example. Find the tangent line to the curve y is equal to the square root of x at x equal to 4. Now we've just calculated the derivative of this function. We know that the derivative of this function is f prime is equal to 1 over 2 root x. And we're interested in this when x is equal to 4. So we need the slope f prime at 4, which is 1 over 2 root 4, or 1 over 4. We want the tangent line when x is equal to 4. If x is equal to 4, then that means y is equal to the square root of 4. So that's y is equal to 2. We want the line which passes through the point 4, 2, and which has slope a quarter. Put these numbers into the formula on the previous slide. The answer to this question is y is equal to 2 plus a quarter x minus 4. Or we can simplify that to a quarter x plus 1. And I can show you a graph of this function and this tangent line. The blue curve is y is equal to the square root of x. The green line is the tangent to the curve when x is equal to 4. Let's talk about notation. There are many ways to write the derivative of a function y is equal to f of x. All of these things mean the same thing. F prime of x, that's the same as y prime. That's the same as dy dx or df dx. That's the same as d dx of f of x. We could also write it as y dot or f dot of x. These mean the derivative of y with respect to x. Now, calculus was started by two men who each claimed that they were the one who invented it, and because of this argument, they grew to hate each other. So Isaac Newton, who was British, used the notation f dot and y dot, which are not commonly used today. Gottfried Leibniz, who was German, used the notation df dx and dy dx, and then the notation f prime and y prime came later from Lagrange, who was Italian. If we want the derivative of y is equal to f of x at a particular point, at the point x is equal to x0, we could write it in any of these ways. We could write f prime at x0, or dy dx at x is equal to x0, or df dx at x is equal to x0, or d dx of f of x at x is equal to x0. So, for example, if we had the function u of x is equal to 1 over x, then u prime at 4, that means d dx of 1 over x at x equal to 4. The derivative of 1 over x is minus 1 over x squared. So this is equal to minus 1 over x squared at x equal to 4. And then we could replace the x by 4 to get minus 1 over 4 squared, or minus 1 over 16. Show that f of x equal to the absolute value of x is not differentiable at x equal to 0. To be able to do this, I need to introduce the idea of one-sided derivatives. Just as we had one-sided limits last week, we can also have one-sided derivatives. The right-hand derivative of f at a is just the definition of a derivative, except instead of h tends to 0, we have the right-hand limit h tends to 0 from the right. Likewise, if we had the definition of a derivative, but we replaced x tends to 0 by x tends to 0 from the left, then we have something called the left-hand derivative of f at b. Okay, so using these ideas, we can calculate the right-hand derivative of our function at x equal to 0. That's the limit as h tends to 0 from the right of absolute value of 0 plus h minus absolute value of 0, just 0, divided by h. We're just doing the limit of h over h, or the limit of 1. Of course, that's equal to 1. You know, because we're doing the right-hand limit, we can always assume that h is a positive number. So therefore, absolute value of h is just h. If instead we do the left-hand limit, then we're assuming that h is on the left of 0. In other words, we're assuming that h is less than 0. If we do the absolute value of a negative number, we get minus that number. So it's going to be minus h divided by h. There's a typo here. This should be a minus. We're just doing the limit of minus 1, which is equal to minus 1. Because the right-hand derivative and the left-hand derivative of x equals 0 are not equal, that tells us that the limit as h tends to 0 does not exist. That tells us that our absolute value of x function is not differentiable at x equal to 0. Let me show you a graph of this function. On the right, on the blue part of the graph, the slope is equal to 1. on the left, where I've drawn the graph in green, the slope is equal to -1. And in the middle, at the red point, when x is equal to 0, the derivative does not exist. So when does a function not have a derivative at a point? If, for example, we had a corner, then we would know that f prime at x0 does not exist. Or, for example, if we had a cusp, then f prime at x0 does not exist. Or if we have a vertical tangent, then again, f prime of x does not exist. If we try to calculate the limit, we would either get plus infinity or minus infinity. So that means that the limit does not exist. If we had a discontinuity like this, then f prime at x0 does not exist. If I had a different type of discontinuity, then again, f prime at x0 does not exist. Why? Well, think about what we were doing about orange lines. We were talking about an orange line like this, which connected 2 points on the curve. And then we were taking the limit as the right-hand end got closer and closer to x0. We would end up with minus infinity, except if we did it on the left, we did the same thing. We would then end up with the left-hand limit is equal to infinity. So at a discontinuity like this, the derivative does not exist. And also, if we had some sort of wild oscillation as we got closer and closer to x0, then the derivative of f at x0 does not exist. Derivative implies continuity. If a function f has a derivative at a point x equal to c, then we know that f must also be continuous at x equal to c. This is an important idea. Anytime we have a differentiable function, we immediately know that the function is also continuous. Or to say it the other way around, if a function is not continuous, then it must not be differentiable. I want to prove this theorem because this is an important theorem. We're going to suppose that f has a derivative at x equal to c. So that means we're starting by saying we know that f prime at c exists. And we're going to use this to prove that f is continuous at x equal to c. Now, what we're going to do is we're going to write h be equal to c minus x, and then I'm going to calculate the limit as x tends to c of f of x. Or the limit as h tends to 0 of f of c plus h. Now I'm going to add something and then I'm going to subtract the same thing. I'm going to do plus f of c and then minus f of c. And then I'm going to multiply and divide by the same thing. I'm going to multiply these two terms by h, and then I'm going to divide them by h. And the reason I'm doing it like this is because then I want to use the sum rule and the product rule for limits to break this up into 3 different limits. The limit is h tends to 0 of f of c. F of c is just a constant, so the limit of a constant is a constant. Plus, this limit I've written in red, the limit is h tends to 0 of f of c plus h minus f of c over h. We know what this red thing is. The red thing is f prime at c. And then finally, we have the limit as h tends to 0 of h. So that's f of c plus f prime of c multiplied by 0 is equal to f of c. This proves that f is continuous at C. Now, let me just repeat this proof. I want to show that the limit as x tends to c of f of x is equal to f of c, because that's what continuous means. And I want to use the fact that f has a derivative at x equal to c. So I want to obtain the definition of the derivative somewhere in my calculation. I want to get limit as h tends to 0 of f of c plus h minus f of c divided by h somewhere in my calculation. So to achieve that, I'm doing plus f of c minus f of c. No change so far. Then I'm going to multiply by h and divide by h. Again, no change so far. We're doing the limit as h tends to 0. So it's okay to assume that h is a small number, but always h is not equal to 0. The sum rule says if we have the limit of a function plus a function, we can cut at the plus and then change it into two different limits. The product rule says if we have a limit of a function multiplied by a function, we can cut between the two functions and have the limit of a function multiplied by the limit of a function. So we can write this as the limit as h tends to c of f of c plus the limit as h tends to 0 of f of c plus h minus f of c over h. And then finally, the limit as h tends to 0 of h. Each of these three limits we know the answer to. We know the value of. The limit as h tends to 0 of f of c is just f of c, because f of c is just a constant. This red limit is the definition of the derivative of f at the value c. This red limit is just f prime at c. And for the third limit, the limit of h as h tends to 0 is just 0. So we have that the limit as h tends to c of f of x is equal to f of c. And this proves that f is continuous at c. Now, let me just note before I go any further, we've just seen that if f has a derivative at x equal to c, then f is continuous at x is equal to c. But the converse is not true. It's not true that if a function is continuous, then it has a derivative. And we've already seen a counter example to this. We've seen that the absolute value of x is continuous at x is equal to 0, but is not differentiable at x equal to 0. And then I come to roughly the halfway point of today's lesson. So I'm going to take a break now until 3 o'clock. I give you a chance to read the necessary sections in your textbook if you wish, or just give your mind a rest. And then we'll do the second half of the lecture starting at 3 o'clock. And now let's continue. Our third topic for this week is differentiation rules. The first rule is for a constant function. If k is a constant, then the derivative of k is equal to 0. I'm not going to be proving most of these. You can read the proofs in your textbook. If n is a real number, then the derivative of x to the power n is nx to the power n minus 1. For example, derivative of x to the power 3, we need to take the 3 down to the front to become 3 multiplied by x to the power 3, and then we decrease the power of x by 1, from 3 down to 2. The answer is 3x squared. We can also use this for derivative of the square root function, which we already know. The derivative of the square root of x, which is the same as the derivative of x to the power of a half, we get a half at the front, and then we decrease the power of a half by 1. X to the power of a half minus 1, or a half x to the power minus a half, which is the same as 1 over 2 square root of x. And that agrees with the formula that we found earlier using the definition which included the limit. Or we can differentiate 1 over x to the power 4, because that just means x to the power minus 4. The derivative of x to the power minus 4, we have a minus 4 at the front, and then we decrease the power of x by 1. So x to the power minus 4 minus 1. That's minus 4x to the power minus 5, or minus 4 divided by x to the power 5. Our third rule is the constant multiple rule. If u of x is a differentiable function, and if k is a number, then ku is also differentiable, and the derivative of ku is k multiplied by the derivative of u. So in other words, anytime we have a constant inside of a derivative, just like if we had it inside of a limit, we could just move that outside of the derivative, just like we can move a constant outside of a limit. This one I do want to prove. And I'm going to prove it using the definition of derivative. The derivative of ku, that means the limit as x tends to 0 of ku at x plus h minus ku at x divided by h. Factor out the k, and then we're going to use the constant multiple rule for limits, which says anytime we have a constant, we can take it outside of a limit. We get k multiplied by this limit, but this limit is just the derivative of u. So just using the definition of a derivative and using the constant multiple rule for limits, we can prove the constant multiple rule for derivatives. So for example, if I want to calculate the derivative of 3x squared, the constant multiple rule says we can take this 3 outside of the derivative. We just get 3 multiplied by the derivative of x squared. So just 3 multiplied by 2x, or 6x. We can do the same thing for minus a function, the derivative of minus u, because that just means minus 1 multiplied by u. Minus 1 is just a constant. Minus 1 we can take outside of the derivative to get minus 1 multiplied by du dx, or minus du dx. Our next rule is the sum rule for derivatives. If u and v are differentiable at x0, then u plus v is also differentiable at x0. And we have the formula that the derivative of u plus v is equal to the derivative of u plus the derivative of v. This one I'm not going to prove. The idea is the same as the last one. We just use the definitions of the derivative, and we use the sum rule for limits to prove that this equation is true. You can read that in your textbook if you want. So, for example, differentiate, that means find the derivative of y is equal to x cubed plus 4 over 3x squared minus 5x plus 1. Using the sum rule and using the previous example about minus 1, we can break this up into 4 different derivatives. The derivative of x cubed plus the derivative of 4 over 3x squared minus the derivative of 5x plus the derivative of 1. And each one of these we can do separately. 3x squared, and then 8 over 3x, and then minus 5, and then plus 0. Does the curve y is equal to x to the power 4 minus 2x squared plus 2 have any points where its derivative is equal to 0? And if the answer is yes, where are they? The first thing to do is to differentiate this function. So here we go. The derivative of x to the power 4 is 4x cubed. The derivative of 2x squared is 4x, and the derivative of 2 is equal to 0. And then I want to factorize this function. First, take a 4x out to get 4x squared minus 1. And then x squared minus 1 is the same as x minus 1, x plus 1. So the question is, are there any points where this derivative is equal to 0? Is it possible to make this equal to 0? Yes. If x is 0, then the derivative is 0. If x is equal to 1, then x minus 1 is equal to 0, so the derivative is 0. And if x is equal to minus 1, then x plus 1 is 0, so the derivative is equal to 0. We can see that the derivative is equal to 0 if and only if x is equal to minus 1 or 0 or 1. And next, I'm going to show you a graph of this function. And we can see from the graph that the derivative, or the slope, is equal to 0 at minus 1, at 0, and at 1. Let's move on to the next rule. The product rule for derivatives. If u and v are differentiable at x0, then their product, u of x, v of x, is also differentiable at x0, and the formula is that the derivative of uv is the derivative of u multiplied by v plus u multiplied by the derivative of v. And this is perhaps easier to remember if we use prime notation. uv prime is equal to u prime v plus uv prime. First, we differentiate the first function, we leave the second function as it is, and then we do plus. And then we leave the first function as it is, and we differentiate just the second function. Let's use this. I've written the product rule in the yellow box at the top. I want to use that to differentiate y is equal to x squared plus 1, x cubed plus 3. And I'm going to solve this example in two different ways. First, I'm going to use the product rule, because we have y is equal to a function multiplied by a function u multiplied by v, where the first function u is x squared plus 1, and the second function v is x cubed plus 3. So by the product rule, differentiate the first function and leave the second function as it is, and then do plus. Leave the first function just as it is and differentiate the second function. The derivative of the first function is 2x plus 0, and the derivative of the second function is 3x squared plus 0. So then it's just a case of simplifying this. We obtain the final answer, 5x to the power 4 plus 3x squared plus 6x. Now let's solve this problem a different way. Another way to solve this problem would be to multiply the brackets out first. We get x to the power 5 plus x cubed plus 3x squared plus 3. And then we can differentiate this directly to get 5x to the power 4 plus 3x squared plus 6x plus 0, which of course is the same answer that we got using solution 1. The quotient rule. If u and v are differentiable at the point x0, and one extra thing we need to be careful of, if v of x0 is not 0, because we can't divide by 0, so just make sure we don't have 0 here, then u over v is also differentiable at the point x0, and we have our formula. The derivative of u over v is u prime v minus uv prime divided by v squared. Now, let me just remind you of the product rule. The product rule said uv prime was so u prime v plus uv prime. In the product rule, we have a plus, but in the quotient rule, there's a minus sign. Okay, I put that formula in the yellow box at the top. I want to use the quotient rule to differentiate y is equal to t squared minus 1 divided by t cubed plus 1. Here we have function divided by function. U divided by v, where u is t squared minus 1, and v is t cubed plus 1. And as long as we're not at t equal to minus 1, v is not equal to 0. So we use our formula. We use u prime v minus uv prime over v squared. So that's derivative of the function on the top multiplied by the function on the bottom minus the function on the top multiplied by the derivative of the function on the bottom, and then divide by function on the bottom squared. Then there's two simple derivatives to do. The derivative of t squared minus 1 is 2t, and the derivative of t cubed plus 1 is 3t squared. And then that's the hardest part of the question done. All that's left in the final two steps on this page is just to simplify this answer as much as we can. I'll leave this for you to check at a later date. Check that we get minus t to the power 4 plus 3t squared plus 2t divided by t cubed plus 1 all squared. Let's do another example. Differentiate f of s is equal to square root of s minus 1 divided by square root of s plus 1. Again, it's function divided by function, so we want to use the quotient. This time, the function on the bottom, square root of s plus 1, this is never going to be equal to 0. And before I use the quotient rule formula, let me remind you that the derivative of the square root of s is 1 divided by 2 square root of s. Okay, so the whole calculation in one go. Let's talk through this. I start with my quotient rule formula, u prime v divided by u v prime divided by v squared. So that's square root of s minus 1 prime, and then v square root of s plus 1, minus, and then u square root of s minus 1, and then v prime, square root of s plus 1 prime, and then this is all divided by v squared, or root s plus 1 all squared. Because the square root of s is 1 over 2 square root of s, and because the derivative of minus 1 or plus 1 is just 0, I get 1 over 2 square root of s, and then square root of s plus 1 minus square root of s minus 1, and then another 1 over 2 square root of s, and then all divided by root s plus 1 all squared. And then we need to simplify this formula as much as we can. And I'll leave the final part of this calculation for you to check. The question from the chat, how did we get a half? So I'm guessing you're talking about this half just here. That's 1 over root s multiplied by root s. The root s cancels with the root s, and we're just left with 1 divided by 2. And then we have 1 over 2 root s multiplied by plus 1, which gives 1 over 2 root s, minus root s multiplied by 1 over 2 root s gives me a half. And then the final term is minus a half, but also another minus, so plus 1. So minus 1 multiplied by minus is plus 1, multiplied by 1 over 2 root s is plus 1 over 2 root s. Plus a half minus a half cancels out. We get 1 over 2 root s plus 1 over 2 root s. Because a half plus a half is 1, that's just the same as 1 over root s on the top. Or we can root s to the bottom to get 1 over root s like this. Let's move to the next example. Differentiate y is equal to x minus 1, x squared minus 2x over x to the power 4. Now again, we have a function divided by a function. So it's possible to use the quotient rule for this question, but there's an easier way. Quotient rule is not always the way that we want to answer these questions. What we can do is we can multiply out the top to get x cubed minus 3x squared plus 2, and then this is all divided by x to the power 4. So this is just equal to x to the power minus 1 minus 3x to the power minus 2 plus 2x to the power minus 3. And then we can differentiate this directly. The derivative of x to the power minus 1. The minus 1 comes down to the front, and then we decrease the power by 1, so it becomes minus x to the power minus 2. The derivative of minus 3x to the power minus 2, we need to multiply this by minus 2, and then we decrease the power from minus 2 to minus 3. So minus 3 multiplied by minus 2 multiply x to the power minus 3, etc. And then we can write that as minus 1 over x squared plus 6 over x cubed minus 6 over x to the power 4. The next idea is the idea of second order derivatives. Remember, if f of x is a differentiable function, then we have a new function called f prime of x. Now, maybe this new function is also differentiable. If that's true, then we can differentiate it, and then we're going to have another new function which we call f double prime. F double prime is called the second derivative of f. We can write the second derivative of f in different ways. We could write f double prime of x, or d dx of f prime of x, or d dx of dy dx, or d squared y dx squared, or dy prime dx, or y double prime. All of these notations mean the same thing. They all mean the second derivative of f. So, for example, if y is equal to x to the power 6, then y prime, that's the derivative of x to the power 6, is 6x to the power 5. And then we can do the second derivative. Y double prime, that means the derivative of y prime, or the derivative of 6x to the power 5, which is 30x to the power 4. There's another way we could do the same calculation. We could write it like this. I could write d squared dx squared for second derivative of x to the power 6. That's the derivative of x6. d dx of x to the power 6. Do the inside derivative first. Derivative of x to the power 6 is 6x to the power 5, and then we differentiate it a second time to get 30x to the power 4. But if f double prime is also a differentiable function, then we could differentiate it to get another new function. Its derivative, f triple prime, is the third derivative of f. If f triple prime is differentiable, then its derivative is the fourth derivative of f. And if the fourth derivative of f is differentiable, then its derivative is the fifth derivative of f, etc., etc., etc. We could say if the n-1th derivative of f is differentiable, then its derivative is the nth derivative of f. Now, you might notice here that the notation changes. For the first three derivatives, I'm using prime notation, and then the notation changes to numbers in brackets. Well, let's suppose we had the 13th derivative. If I wrote, or if I said f prime, 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 that would just be silly. So instead we write the number 13 in brackets instead of writing 13 prime symbols. For example, find the first 4 derivatives of y is equal to x cubed minus 3x squared plus 2. First derivative is easy, 3x squared minus 6x. And then we want to differentiate it again to get the second derivative. The derivative of 3x squared minus 6x is 6x minus 6. And then differentiate it again. The third derivative is y triple prime is equal to 6. And then the fourth derivative of y, the derivative of 6 is just 0. Now that's all we were asked for in the example, but note that because the derivative of 0 is equal to 0, that means that the fifth derivative, the sixth derivative, the seventh derivative, the eighth derivative, etc., also all equal to 0. Our final topic for today's lesson is about the derivative as a rate of change. The rate of change of f with respect to x at x0 is just the derivative f prime at x0, provided the limit exists. Rate of change is just another way of saying derivative. So for example, the area of a circle is related to its diameter by the equation area is equal to pi over 4 diameter squared. The question is, how fast does the area change with respect to the diameter when the diameter is 10 meters? The question is asking us to calculate dA dd, the derivative of a with respect to d, when d is equal to 10 meters. So we do our calculation. We want to calculate dA dd. So we differentiate our formula with respect to d, pi over 4 multiplied by 2a, or just pi d over 2. What is this rate of change when d is equal to 10 meters? We get 5 pi meters squared per meter. We can also talk about motion along a line, displacement, velocity, speed, acceleration, and jerk. Let's suppose we have some object which is moving along a line. Let s, which is a function of t, be its position at time t. We can ask, how far has the object moved if we go from time t to time t plus delta t? This is called the displacement of the object. And we know that this displacement is f at t plus delta t minus f at t. Its new position minus its old position. We might ask, what is the average velocity of the object between time t and time t plus delta t? To answer that, we do displacement divided by travel time. So delta s divided by delta t, or f of t plus delta t minus f of t divided by delta t. And this looks familiar to you, I hope. What do we get if we take the limit as delta t tends to 0? We find that velocity is the derivative of position. More precisely, we find that the velocity, which I'm going to call v of t, is ds dt. Sometimes we don't want velocity in terms of which has its direction, which has positive and negative. Sometimes we just want speed. Speed means the absolute value of velocity. Speed is the absolute value of ds dt. And then we can go further. If velocity is the derivative of position, what is the derivative of velocity? The derivative of velocity is called acceleration. Acceleration, or a of t, is the derivative of velocity, or dv dt. And what is the derivative of acceleration? The derivative of acceleration is called jerk, or j of t. That's dA dt. My next example involves a stick of dynamite and a rock and an explosion. A dynamite blast blows a heavy rock straight upwards with a launch velocity of 49 meters per second. It reaches a height of s equal to 49t minus 4.9t squared meters after t seconds. And then I want to answer 4 questions. Question 1, how high does the rock go? Question 2, what are the velocity and speed of the rock when it is 78.4 meters above the ground on the way up? And then same question, but on the way down. Question 3, what is the acceleration of the rock at time t during its flight? And then question number 4, when does the rock hit the ground? So to recap, we're starting with a rock on the ground sitting on a stick of dynamite. The dynamite is going to explode and the rock is going to be thrown upwards. When the rock is 78.4 meters above the ground, we want to calculate its velocity. At some point, it will get to the top of its flight. We want to know what is the height of the rock here. And then the rock will start falling down again. When again it's 78.4 meters above the ground, we want to calculate its velocity. And we want to calculate when does the rock hit the ground? What is the time when the rock hits the ground? Okay, so what are we told? We're told that its position, s of t, is 49t minus 4.9t squared meters. We can get its velocity by differentiating this. The velocity is the derivative of position, so 49 minus 9.8t meters per second. Let's answer the first question. How high does it go? Well, when it gets to the top of its flight, it's not moving. When it's at the top, it's going to have velocity equal to 0. When do we have velocity equal to 0? We have velocity equal to 0 when the time is 5 seconds. And then we can calculate the height of the rock after 5 seconds. Stick the numbers in and we get 122.5 meters. So the height of the rock, the highest point is 122.5 meters. Let's fill that in. The second question was about the velocity of the rock when it's 78.4 meters above the ground. So how can we get position equal to 78.4? So in other words, when do we have 49t minus 4.9t squared equal to 78.4? Rearrange this equation and we get to 4.9, t minus 2, t minus 8 is equal to 0. So that means the rock is 78.4 meters above the ground when the time is either equal to 2 or the time is equal to 8. And what is the velocity at these times? The velocity at time 2, 49 minus 9.8 multiplied by 2 is 29.4 meters per second. And then on the way down again, the velocity at time 8 is 49 minus 9.8 multiplied by 8, which is minus 29.4 meters per second. The speed means absolute value of velocity. The speed at both of these points is 29.4 meters per second. Question 3 was about the acceleration of the rock. Acceleration means derivative of velocity. So we take our formula for velocity and we differentiate it to get acceleration is minus 9.8 meters per second squared. Question 4. When does the rock hit the ground? We want to calculate when the position of the rock is equal to 0, when it's on the ground. And we can factorize this to 4.9t, 10 minus t. When is this equal to 0? It's equal at start when t is equal to 0, and it's also equal to 0 when t is equal to 10 seconds. So that tells us the rock hits the ground after 10 seconds. And my final idea for this week's lesson is about using derivatives in economics. Let's suppose that C of x is the cost to produce x tons of steel in 1 week. Now, of course, if we want to produce more steel, then it's going to cost more. How much does it cost more? It's going to cost C of x plus h minus C of x more. What is the average of this? Divide by h. The average cost of producing each additional ton is going to be Cx plus h minus C of x over h. And then if we take the limit as h tends to 0, we get something called the marginal cost of producing more steel per week. And that is just the derivative of C with respect to x. So basically, we're doing economics and we're using derivatives. For example, suppose that it costs C of x is equal to x cubed minus 6x squared plus 15x liras to produce x radiators per day, as long as x is between 8 and 30. And suppose that you earn R of x is equal to x cubed minus 3x squared plus 12x liras from selling these x radiators. So C of x is the cost of producing the radiators and R of x is the return from selling the radiators. And we're going to suppose that your factory currently makes 10 radiators per day. Question 1. How much extra would it cost to produce 1 more radiator per day? And question 2, how much more profit can you make by producing 11 radiators per day instead of 10? And we're going to answer this using derivatives. We want the marginal cost of production. That's the derivative of cost. And we want to calculate this when x is equal to 10, when we're making 10 radiators. C prime of x is 3x squared minus 12x plus 15. So C prime when x is equal to 10 is 195. And the marginal revenue is the derivative of r, so 3x squared minus 6x plus 12. R prime at 10 is 252. So that means producing 11 radiators per day instead of 10 will cost approximately 195 liras extra, but it will bring in approximately 252 liras more. So we would expect your profit to increase by approximately 57 liras. And that's all I'm going to do about economics in this course. Next time, we're going to finish talking about derivatives. We will do derivatives of trigonometric functions, the chain rule, and implicit differentiation. Are there any questions?